Hello, everyone, and good morning to you all. Thank you for joining us for the webinar on direct electron TEM cameras for life science applications. For people who don't know me, I'm Kamran Khajapour. I work as microscopy and microanalysis product manager with AXD. I'm very pleased to open the introduction to this webinar today, conducted by us and our partner, Direct Electron from the States. So for people who don't know AXD, we are Australia's largest independent distributor for high-tech scientific instruments. We have a very large product range covering microscopy, microanalysis, nanofabrication, nanotechnology in both material science and life science areas. We actually take pride in building a strong relationship with our customers and suppliers, bringing together the best in scientific innovation and research with the cutting-edge scientific instrumentation and characterization techniques. So today's talk is all about life science applications of our TEM camera range. And our speaker is Dr. Michael Spillman, who is an application scientist with Direct Electron in the States. So Michael received his PhD in biochemistry and molecular genetics, focusing on high throughput methodologies. After finishing his PhD, he joined Scott Stagg at Florida State University to work on imaging small biological macromolecules. He's broadly interested in applying novel imaging methods using direct electron detection cameras to bridge high-resolution biological structures with real-time dynamics. At Direct Electron, he delivers both on and off-site services to support new and existing customers and collaborate with them on numerous projects, including working on single particle cryo-EM, micro-electron diffraction, and liquid cell in situ. So he will be conducting the talk from now on. Just before starting, I'd like to let you know that we have a question and answer button in the bottom of the screen, as you can see. So anytime during the presentation, if you had any question, please type it in there. Michael actually will stop during the talk and answer the questions for everyone. So any question actually would be great because it can be a question that others have as well, so it can be answered all together. Without wasting more time, I'm going to actually hand it over to Mike to start. So over to you, Mike.
All right, thank you so much for the introduction, and good morning, everyone. So I'm Michael Swillman, and talk a little bit about direct electron cameras, our philosophy, work, and applications for life science. So, from sort of entry-level microscopes to very high-ends, like Titan lenses and JWEL, cryo arms. All right, so direct electron, we've been around since 2007, and so our very first commercial product was the DE12, and we still have the DE12 around sort of as our baseline product, but it has been sort of upgraded and revitalized as the DE DirectView, which we'll cover a little bit later. We also make low voltage series cameras. This is sort of your 10 to 40 kV range, and we also make software to control our cameras. Most of the people who use our cameras are using an automated software such as Leginon or Serial EM. There's even EM Menu and EM Tools from TVIPS. So a little bit about direct detectors. I don't know sort of the audience that we have here today, but I just want to go a little bit about, if you don't know what a direct detector is, this is a sort of an introductory slide. So essentially with, anything fiber coupled or lens coupled, with a scintillator or fiber optic bundle, you have either a CCD or a CMOS detector, and that's sort of the old way of doing things. You'd convert the electrons to photons using a scintillator, and then you'd image those directly onto whatever the sensor is underneath it. Previously CCDs, now mostly CMOS detectors. And the big problem with that is that you're really limited by the performance of the scintillator and its efficiency of converting electrons to photons, as well as the fiber optic coupling and things like that. So you end up with this point spread function. With direct detectors, you don't have any of that on top. It is basically just a piece of silicon that sits out inside of the microscope vacuum, and you image directly on those pixels. There's no conversion from electrons to photons or anything like that. And the big benefit of that is you get really high resolution signal. There's much lower noise because these are much colder than typical CCDs and CMOS detectors with fiber optics on them. And it's really led to this resolution revolution. So the very first direct detection paper was back in 2011. And so this was in JSP, and this came from Bridget Kerrigan.
She was all over. Is it her daughter?
And so this is the sort of the very, very beginning of it. And this is using a DE12 on a FEI Techni F20. And we can see here from this graph, this is essentially where everything began. So we can see that we've got 2, 3, and 4 angstrom structures in the EMDB. And we see that the first deposition was basically in the middle of 2011. And since then, basically everyone's gotten a direct detector, and just the number of 2 angstrom, 3 angstrom, and 4 angstrom structures has absolutely exploded. So it's really, the detectors themselves have led to this massive outpouring of data and high resolution information as well. So we have 3 cameras that are primarily for cryo-EM. So we have the DE DirectView. This is our entry-level 12 megapixel camera, and it's really sort of targeted for entry-level life sciences as well as in situ for material science. For sort of a step up from those two, our 2 latest cameras are the DE16 and the DE64. So the 16 is 16 megapixels, and the 64 is 67 megapixels. So it's an 8K camera. And they're the latest and greatest technology that we have. And they've got much higher frame rates. They're way more sensitive. They all do counting. So I think I saw a question. So what do we call entry level in terms of TEMs? So entry level, I would probably say, is a 120 kV Lab 6 filament microscope. So this would be like your 1400 plus. If you have like a Techni T12, those kind of things. Intermediate, that's not an FEG, would probably be something like a 200 kV Lab 6. So that would be like the old Spheres. I guess there's some 2100 Lab 6 microscopes from JOL. So the first thing we'll talk about is the DirectView, and this actually gets into the sort of this entry level question that we have. And for a long time, there haven't been there haven't been any high resolution structures that have come from 120 kV instruments. And that there's a recent paper from Richard Henderson talking about the possibility of using a 120 or 100 kV FEG instruments to get to extremely high resolutions relatively quickly. And so there's that's still, as soon as you have a FEG source, then your microscope's not cheap anymore, regardless of what the accelerating voltage is. But things like the 1400 plus or 1400 flash now, and the other 120 kV Lab 6 instruments, they're a lot cheaper, they're a lot more affordable, and there's a whole lot more of them too. And I know a lot of people use them for screening and things like that. And for lots of labs that need to do screening, or even get low resolution structures, or even good 2D class information, these microscopes are the workhorses. This is where everyone goes to mostly start their imaging, to see what their samples look like. And it would be really awesome if someone made a camera that worked really well at 120 kV on these instruments, so that you could get, say, nanometer resolution. And so we can see that that there's only one unpublished structure at better than a nanometer resolution, and that's actually from one of our cameras on a 120 kV Lab 6 microscope. So if we take a look at from the DirectView, if we just look at carbon film, obviously this goes back to the history of direct detectors. One of the big benefits is you get the frame information out of it, and so with those frames you can then motion correct and of course recover all of your information. And so even at 1.5 microns defocus on a Lab 6 instrument, if there's motion in it, again, much like any source, you're not going to get a whole lot out of the image. But if you use motion correction, then you can get quite a lot of information out of it. And this is especially so if you're using even closer to focus imaging, which you'd have to do with a Lab 6 instrument. And you get quite nice signal to noise out of the DirectView. And this is one of the major benefits. And so what our head of research and development, Benjamin Mamas, did is he sat down at a 2100 Lab 6 that had been set to 120 kV. Is he collected some data on about an hour's worth of data on this MMCPN, and it's basically a small spherical structure. It's basically a little cage, and sat down 1 hour, manual data collection, collected about 66 images, and I think about 20,000 particles, on this Lab 6 instrument, and had no problem getting to 10 angstroms. And for a lot of people, this is huge. I mean, if you can, take your sample and at least, see, to get to, 10 angstrom resolution is huge. And, this opens up the door for lots of screening, so you can, prove that your sample is good, that you've got, at least a structure that looks good, and, go from there to a 200 or 300 kV microscope with a FEG on it. So the DirectView is really, as I said, it's our entry-level camera, and it's it may be entry-level, but at the same time, it's still a direct detector, and it is really, really good at both 200 kV and 300 kV, but it really shines at 120 kV for these entry-level microscopes. You can turn something that's just been used for negative staining into something you can use for regular data collection for your initial models. And it's I'm not in in terms of sales or anything like that, but the DirectView is essentially priced at the level of in the range of a Gatan 1 view, and so you can basically get to the 1 view price, but you get a direct detector out of it. So I see a question, have we tried on a 120 kV tungsten filament? The answer is yes. The big problem with tungsten is it's really, really incoherent. And we have not had good results with tungsten. You pretty much have to have Lab 6. It's just, tungsten is pretty bad. We actually have a camera that we've been testing on a tungsten filament and have not had good results from it. Lab 6 is pretty much required for a direct detector. So from here on out, the next large sections will be about the DE16 and the DE64 cameras. And so there are sort of, our high-end cameras that are targeted for, electron counting and things like that. First, we're going to cover a fair bit about how detectors work and what are the sources of noise and electron counting and things like that before we sort of get into some of the results. But we'll actually start with high resolution single particle, which is what a lot of people are in the market for today. And so this is from the University of Glasgow out of David Bella's lab, and this is from a JOL cryo-armed 300 with a DE64 run in counting mode. And this is Luzemann synthase. It's about 2.25 angstrom resolutions. It's from about 20,000 particles, and I think they collected for either 1 day and 1 night, or maybe it was 2 days total. And this is one of their highest resolution structures that I think they got this earlier this year, and just shows you that our counting software works quite well, and we can get a really, really high resolution very quickly. So we can even see, the side chains look very, very nice. We can see, the holes in the aromatic rings. We can see water molecules in it as well. So we're quite pleased with, the way that the DE64 works for counting, and the DE16 as well. They're technically identical to each other in terms of the pixel architecture. It's just that the DE64 is 4 times larger than the 16. So now the next couple of slides, and if anyone has a question on sort of the imaging theory and things like that, this is a lengthy section on how our detectors work and how direct detectors work in general. And one of the major benefits from having a direct detector is this modulation transfer function. And this is essentially how well can you represent a signal at various resolutions. And so the finer the spacing is in this gradient, really, basically this is the resolution, how faithfully is that represented in terms of signal. And as you get finer and finer spacing units, you can see that the signal goes down, and that's true for all cameras. The big difference between direct detectors and anything with a scintillator, whether it be CCD or CMOS, is this massive increase in MTF. And so on the bottom in orange, we have this fiber-coupled CMOS MTF, and just the regular DE16 running in integrating mode. The MTF, you can see, is about 3 times higher across all spatial frequencies. And this is true for most of the direct detectors. There's this really, really, really high increase in MTF. And that's basically the resolution of the sensor. And if you're talking about resolution, then you also need to talk about signal to noise. And that's when this DQE comes into effect, and that's this detective quantum efficiency. So this is how well does the detector faithfully record the input image without adding more noise at various resolutions. And of course, a very large part of that is, in fact, the MTF. And there's also the noise power spectrum and various other things. But this is sort of the, people will ask, what's the DQE? And this is about a little bit about how that's important. So with compared to a fiber coupled camera, there's about a 4x increase, about 3.8 increase in like the DE16 at 300 kV. And this is just in integrating mode. So we'll talk a little bit about electron counting coming up. So with electron counting, you have several different approaches. There's the black box method, which is typically what the other competitors use, and then there's the way that we do it, and the way that we do it is fairly open. But the counting in general is essentially the same thing. You have the raw image from the camera, which is represented on the far left with the raw frame. You then basically subtract the dark image from it and do thresholding. And thresholding is essentially, you try and set all of the background events that are non-electron strikes to 0. And then once you've centroided or identified all of the, electron events, that gives you your counted frame. And you take the counted frames and add them all together, and that gives you an image that you can actually, see. So that would be maybe your dose fractionated image, and then you would take all of those frames and then align them together to get the actual total exposure. So to give you an idea, this is actually a material science slide, but I think it represents pretty well, how important electron counting is. And on the left-hand side, we've got a conventional, fiber-coupled CMOS. On the right-hand side, we have one of our DE cameras. And both of these images are of zeolite. This is sort of like the material you might find in, your cold holder. And, both have about 2 electrons per square angstrom total dose. And so you can see the difference with electron counting is that, you can then really see, the atomic structure of the zeolite material. And on the left-hand side with the conventional, fiber-coupled camera, it's pretty blurry. There's not really a whole lot of information because there's so much noise in the image. So there's a whole lot of sources for noise in direct detectors. And so we'll talk about sort of one after another and how they affect, different products and, how we deal with it. So the first one is actually shot noise. And so actually all cameras, all direct detectors have this inherent problem of that there's sort of a random number of electrons that typically hit the camera at any one time. So that's the shot noise. And there's no true way to sort of deal with that other than, dialing down the dose. So spreading your beam, making it less intense. But they also have to deal with this stochastic scattering. So this has to deal with how the electrons interact with the pixel itself. So this is a cartoon of a CMOS sensor, or CMOS pixel. And the important thing to look at is the particle track. And so that's this big black line that sort of goes down the middle of the pixel. And electrons are really poorly behaved in these CMOS pixels. They sort of enter in and can either bounce around inside the same pixel, they can go straight through it without leaving any signal, they can enter in one pixel, leave signal, and continue on and actually exit out another pixel, leaving even more signal. And so, this is the stochastic, interactions that all of the sensors have to deal with. And if you have big pixels or small pixels, you can do various things for to have better counting or do super resolution, that kind of thing. So we take a look at individual electron events. This is an image that has inverted contrast. So the electron strikes are in essentially black, and backgrounds, nothing is in white. And so we can see that there are small events, large events, there are streaky events, and so this is what you would get from basically a counted frame before you start after dark subtraction. And the real hard part about electron counting is that because they're poorly behaved in the silicon itself, it's difficult to say, what pixel did it enter? If it entered one pixel, did it actually go in that one, or did it come from another adjacent pixel? And so if you have real streaky events, then you sort of have to guess where the center of it is, and this can lead to performance degradation and sort of other issues. So one of the important things to do is to figure out how to match the electron event size, the electron blobs, to the actual physical pixel size. And when you have events that are in a single pixel, there's no uncertainty. The event is in one pixel, and that's where the electron went. So if we were to use this example here, this is from a DE64, that's most of these events are about 1 to 4 pixels. So if we have events that are 4 pixels in size, then it's pretty easy to determine where it came in if you're going to do what we typically do, which is we use hardware binning. And this is essentially using 4 pixels on the camera to create one large pixel. And the benefits of this is that if you use a large pixel, so if you have an event that's in 4 physical pixels, and then you do hardware binning, and then the signal is only in 1, then there's no question about where the event is. And so when you do this, and you do counting on that using large physical pixels, you essentially get, with our camera, the DE64 and the DE16, a near perfect MTF. And so pretty much nobody else does this because typically people will say binning is bad. That is true if you're doing software binning because you can have aliasing artifacts. But if you do hardware binning, then when it's all on the sensor, it's all in the pixels, then there's no extra noise added to it. There's no readout event changes. It's basically the 4 pixels are then summed up into a single pixel. And so we can actually see this, the way that MTF works, as you remember seeing, in that as you get finer and finer striations in it, that's really where you start to see the changes in resolution. So in this image on the left, we can actually see this is the edge of a beam stop, and you can actually see where it is in register and then slightly out of register with the pixels themselves. And so you can see it go from completely black to having an edge of signal, and then you can start to see it sort of being a little bit fuzzy, and then it goes back to being completely black. And so this is where you basically see MTF differences. And so this is this hard edge, and there's a complete difference between no signal and signal. And as you have it go across the pixels, you can see that the signal goes down when there's a little bit of it obscured. So that was all about stochastic scattering. Then one of the other components is Landau noise. And so this is the probability of the electrons leaving a certain amount of signal in each pixel. And to make a long story short, talking about these single electron events, all cameras, all direct detectors have exactly the same sort of normalized Landau distribution. So the electrons typically deposit exactly the same amount of energy in each pixel. So the probability of that, you have mostly no signal is pretty high, and then the amount of signal that's left as it increases goes down. So all these detectors essentially have the same sort of behavior for Landau noise. So that also brings into the effect that you have reset noise, and this is what a lot of people are talking about now. And I know some other people have been doing it for a while off chip, and more recently one of the other competitors has it as well off chip. is what we call correlated double sampling. So a typical CMOS pixel design, so this would be your anything from Thermo, anything from Gatan, pretty much anybody else that makes CMOS detectors, is you have 3 pixels, or you have 3 transistors in each pixel. And there's 3 events that happen. You have a reset event where the pixel value is essentially reset to 0. There's an acquisition step where the electrons are hitting it. And then there's a read event. And so that's when the value of the pixel is read out. The issue is that when you do the reset on a CMOS pixel, it doesn't always go to 0. And if you assume that it always goes to 0, then you're either losing signal or you're adding noise to it. And that's not good. So this is, again, we're talking about, sources of noise, and the less noise you have, the more accurate your counting can be and the higher resolution your data. So the way that we do it is we do correlated double sampling on the sensor itself. So this is all in the physical pixels. So we have additional transistors in our pixels, and what we do is that when there's a reset event, we actually read the value in the pixel after that reset command. Then when there's the acquisition period, when that is read out, it's essentially subtracted. You take the stored value from the reset and subtract it from that read value. And you do that every single time that pixel is read out. And you're essentially creating a noise floor that changes so that you're not adding or losing signal to that because of the way that these pixels work. And this is all CMOS detectors that have this reset noise. And with correlated double sampling that we do on the sensor, then you really limit that amount of signal, and that can be the difference between having your threshold for counting be 18 counts or 25. And it may seem like just a few counts, but when we're talking about very little signal being left in each of these pixels for counting, that makes a big difference in performance. And talking about differences in signal to noise. So on the left-hand side, we have a competitor's camera. And on the right-hand side, we have a DE20, which is very, very similar in terms of performance to the DE16 and the DE64. And the single incident electrons is about 2.5 times more signal to noise in the DE20 versus the competitor's camera. And so this makes a really big difference when you're doing counting. It's really easy to identify what electrons are actually events over the backgrounds, and you're not losing, counts, and you don't have false positives. So that brings us to, how do you determine the optimal threshold for counting? So this is a lot of going on in this figure here. So the idea is that if you take a look at most of the electron events, they will leave, a fair bit more signal than there is background. But it's really, it's really important to remember that, with the Landau distribution of, the energy that's left is there's a lot of it that's, sort of very low, low signal that's left. And if your background is very high, then, you're going to either lose events or you're going to add noise because you're going to be picking up things that actually aren't electron events. And so with, the correlated double sampling that we have, using hardware binning, then these events are really easy to find, and we can set the threshold for counting ever so slightly above the backgrounds, and so we're essentially going to be able to detect 99.8% of all the electron events that we can see, because all the detectors, regardless of who makes them, if an electron doesn't leave any energy, then nobody can detect it anyway. So these are all about detectable events. And so, being able to have a really tight threshold allows you to get, the maximum amount of signal out of the camera so that when you are counting, you really are finding all of these events. And this comes back to, if you have low noise, you have, high accuracy counting, you're doing this hardware binning to localize your events to single physical pixels. Then taking a look at DQEs for integrating mode is this one in the bottom in blue. So that's D16, D64 integrating mode. When you're doing counting, if you're just doing the full sensor size, you're not doing any of this fancy hardware binning, then the yellow line is going to be sort of for your counting performances in terms of DQE. But if you do the hardware binning, so essentially with our cameras, they have 6.5 micron pixels, then you're using actually a virtual 13 micron pixel, then the performance boost is even greater in terms of DQE. It's about 9 to 10% off the theoretical maximum DQE that you can have for a pixelated detector. So this is extremely high performance. I don't think anyone has a camera that's a large physical pixel array that comes anywhere close to this particular kind of performance. So this is actually our DQE curve. The folks at Florida State from Scott Stagg's lab have actually done another DQE curve with their own DE64 and found it to be essentially identical to ours. So a little bit about results. Speaking of Florida State, one of the things that they have is they actually have a K3 on the bioquantum and along with a DE64 pre-GIF. And they were kind enough to do some comparison studies for us. And so their sample of choice here is albilase. This is a fairly small 144 kilodalton protein. I suppose nowadays it's pretty large. But of course they have a Titan Krios 300 kV. They use Leginon for all of their data collection. And they collected for, I guess, a couple of hours on both the DE64 and the K3. And the data from the DE64 looks absolutely wonderful. And they get tone rings all the way up to the edges. And let's talk about performance comparison. So on the left-hand side, we have the DE64 results. On the right-hand side of the K3, operated in zero loss imaging mode on the bioquantum. So the big takeaways from this figure right here is that the DE64 is significantly slower than the K3. The K3 is extremely fast. They get about 3 times more particles per hour than the DE64. However, as they found out, you can't actually collect enough data fast enough to outrun performance. And that's exactly what they ran into, is that no matter how long they collected with the K3, they can never get to a higher resolution than the D64 could. And they were sort of sample limited in terms of their resolution results, but still 3.1 versus 3.5 on the K3 is nothing to scoff at. And I think the mean CTF res for each image speaks volumes in terms of the performance of the cameras. Getting 3.6 angstroms on the D64 versus 4.5 on the K3. So here's one of the very few microscopes that has both counting cameras and a good head-to-head study. Our philosophy in terms of lowest noise, the best signal-to-noise ratio, doing electron counting with hardware binning, it really pays off. And it's really important that this gets out there and that people see that there are alternatives to Gatan and FBI cameras. And so with, of course, the DE64, it's an enormous camera. I mean, this is 67.1 million pixels, and it makes it really easy to do all your screening on, do your montages in just a couple of images. You can do large scale data acquisition, even in integrating mode if your target's like say 4 or 5 angstroms. Integrating mode can be nearly as fast. And taking 1-second exposures and getting 4.5 angstroms pretty quick. It's a really huge, really flexible camera for life sciences. So I will pause here and see if anyone has any questions for just a moment about this quite large amount of information in terms of how we handle imaging and noise and things like that.
Can't see any question in the question answer box as well, so maybe no question.
Okay.
Oh, there is a chat coming.
Yep. It's the order of installation with other cameras. Typically what we do is that at the moment we don't have any compatibility with the of course Gatan energy filters. There is one example that of a Gatan GIF that has a DE camera on it, but that's sort of a special case. But most of the time, you'd find the DE cameras in the same location as like the Falcon or you're going to find it in the pre-gift box. Typically, because our pixels are smaller, then they're small like, the Gatan products. Normally what you would do is if you have, if there's not a GIF and you have, say, like a CETA camera or a Falcon or something like that, we like those to be on the bottom or below our cameras because I have the smaller pixels deal better with less post magnification. Yes, so in fact, we can pretty much any of the, as long as there's not a GIF, we can fit below either the Thermo CETA box or Falcon box, as well as the older and even the latest Gatan boxes. So we prefer to go into being above any of those cameras, but there's really no problem with us putting our housing below them.
So there is a question in the question answer box as well.
Yeah, so I see from James. So is the DC4 such a great performer by bending by 2x and turning this into a 4K system with large pixels? The answer is yes. So basically what you're doing is you're taking the 8K by 8K image, and from the sensor it is then read out as a 4K by 4K. And there's two benefits from this. One is the increase in performance, but you also end up with a much higher frame rate. So the native frame rate of the DE64, the 8K images, is about 42 frames per second. When you do the hardware bending by 2, you essentially end up with 141 frames per second. And so this makes exposures for counting about 10 to 12 seconds in total. And you end up with about 2 electrons per pixel per second is the exposure rate. You can still do 8K counting. It's just that you're like the Falcon 3 counting, you're very limited by how stable your microscope stage is. So if there's any drift in it, at 40 frames per second, 42 frames per second counting, if there's any drift in it, typically the image is not going to be good. So for, that is something I did not mention. So in terms of integration with other software, there's no integration at the moment with EPU. We've asked and had discussions with Thermo about that, but as far as I know, no progress. But with JADIS, yes, we're completely integrated into JADIS. And in fact, at Glasgow, University of Glasgow, that's pretty much all they use to collect their data is they do everything with JADIS. Serial EM as well, totally integrated into that. In fact, we work closely with David Mastronardi to implement new features into Serial EM as we add them to our camera. Legend as well. So Scott Stagg at Florida State and even Bridges Group in YSBC, they've got a DE20 there. And so we work closely with them to make sure that, as we come out with new features for the DE cameras, again, they're integrated into that software as well. Can we put one of these on the end of a GIF? The answer is yes, but not from Gatan. So if you haven't heard, CEOS, the corrector maker, is actually going to be releasing a energy filter themselves. I think next summer is when it's coming out. And it'll be both for life sciences and material science. But yes, we actually have a camera in their factory that they're using to make sure that we're fully integrated into their systems. And they say that their goal is to have better performance than the Gatan system, and if their correctors are any indication of that, I think they have a fairly good shot at meeting that goal. So. And we have talked to them extensively about the 8K camera, and the aperture size on the end is sufficiently large enough for the entire field of view of the DE64 on the CEOS energy filter. There's more that's going to be coming out about that in the next, probably in the next year, but they'll talk more about it when they're ready. And as far as I know, they'll be compatible with everybody's microscopes. Thermo and JOL, I guess Hitachi as well. There's no other questions at the moment. We'll continue on.
The last question from Eric in the chat box.
So let's see. Yeah, I discussed the CD or the OneView. Okay. I did talk about the integration with JADIS, Serial EM and Legend, and we're also integrated into EPU. As I said, we're not integrated into that. It would be nice, but again, it's it's more of, does Thermo want to let us work in their software? And so far, I guess the answer is no. So I guess the next part of this talk will mostly focus on some of the other applications that have been going on, including tomography and micro-ED. Again, some of these things are fairly new that we're working on, and if anyone has any questions, sort of just interrupt me or just ask the question, and I'm happy to stop and answer it. Okay, so as I said, we're going to go to tomography now. So the 8K field of view on the DE64 gives you a huge, huge field of view. In this case, this is from the folks at Baylor College of Medicine in Houston, Texas. And this is on their JL 2200 FS. That's, oops. There we go. And so this is some rod cell fragments from a wild type mouse, and basically they get a huge field of view, and without any, they don't have to compromise on field of view versus resolution. So I mean, the inherent low dose of tomography is always an issue. Even integrating mode works really, really well for tomography in this camera, and they don't have to sacrifice field of view to keep the dose rate down. And at the same time, they get all that context. When you're talking about, large assemblies like this, context is important. And so getting such a huge field of view is really, really important for tomography. So we can see they add up a couple of frames, and it looks quite nice for the reconstruction. And you can see all the segments in it. So one of the things that we have been working on recently, I know that some people have talked about it as well, I guess on the Serial EM list server, is continuous tilt tomography. And so this is the idea of tilting your stage all the way up at 60 or 70 degrees, and just recording all the frames as they come out, and just tilting your sample all the way to either plus minus 60, plus minus 70, without stopping. And the huge benefit of this is time. Normally, it's going to take somewhere between 15 to 30 minutes to take one tilt series. So this is from the folks at Stanford. This is at Slack, and this is on a Talos Arctica with the D64. And basically, it took them 2.5 minutes to take this entire tilt series. It was about 1,500 frames. It's about 0.08 degrees per frame. And you get a 3.1 micron field of view. This is without an energy filter. This is more to sort of showcase the concept of doing this continuous tilt tomography on our cameras. So there's no real limitation on the length of exposure you can take, other than basically how much memory is in the system for our cameras. And so you can take really, really long exposures all at once, and just have massive, massive throughputs in terms of how many tomograms can you get out in an hour. And we take a look, we have a single frame. You can see some information in it. It's not super intense, but add up 35 frames, and it looks really, really nice. And so this continuous tilt tomography was actually done all in Serial EM. They basically wrote a script for it, and it did it all by itself. There wasn't much to it. It's the biggest things would be, if you're using whatever, if you have a side entry microscope, stage stability is probably the biggest limitation. Otherwise, of course, if you're using phase plates, just the length of exposure can have some issues. But imagine being able to automate your tilt series and take 20 of these an hour. So this was sort of the statistics from their continuous tilt throughput. About 2.5 minutes for the acquisition. It's a minute worth of overhead. Let's see. So the question is, are we releasing and managing serial EM scripts? So the answer is we're not managing them, but we're working closely with all of our customers, that are interested in this to, make sure that it can work and, make sure that the camera side of things doesn't have a problem. Because basically the only thing that you have to do is for the serial EM scripts, they're not technically limited to like a DE camera. You just set up your exposure acquisition and tell it to take, this continuous tilt, and that's pretty much it. So for basically, in about, this is about 6 minutes, 5 minutes, you can take an entire tilt series and, collect the next one right after that. It's about 144 tilt series in 12 hours. Keep all of your grad students and postdocs busy for months and years. Okay, so the big advantage for the DE64 obviously is absolutely huge. That's a huge field of view and the high throughput using this continuous tilt tomography methodology. I mean, you can just let this thing go, and if you have batch tomography set up, just collect hundreds of these things every hour. So the next topic we'll talk about is micro ED. So this is a big hot topic by a lot of people. I know Tamir Gonen has sort of made this all the rage in terms of, how high of a resolution can we go with an electron microscope, and what samples can we dig out of our fridge for the crystallographers that only made small crystals, and how far can they go? So this is from Stanford as well. It's SLAC. So this is also on the Taos Arctica, and this is biotin. So they basically just bought biotin and crushed it up into a powder, put it on the grid, and stuck in the microscope and cooled it down. And this is using the DE64, and they're using. There's a couple of things that they did that we haven't talked about in terms of what our hardware can also do. But if we take if we take just a couple of frames and add them together, we can see, really nice bright spots all across the sensor. Their final resolution for this was 0.7 angstroms, and this was the very first attempt. So, excuse me. So this was brand new for all of us, and we weren't sure how well this was going to work, but as it turns out, it works really, really well. So again, this was also done in serial EM. So this basically just told serial EM to do a tilt series for in diffraction, and we collected the entire tilt series. So I'm not a crystallographer. I'm interested in like virus structures, but not crystallography. So all I know is that 0.7 angstroms is pretty high resolution. The dose for the total dose for this micro ED experiment was about 3.6 electrons per square angstrom, which is probably a little bit high in terms of most micro ED experiments, but it still is a fairly low dose, so compared to what most biologists are working with. So the total time to get a structure out of this is sort of optimized. Of course, the tilt series collection is about 3 minutes for this to do sort of this processing of these frames from the camera. We have our own script that we've written, and that one we're actually maintaining is about 10 minutes of processing time in that. Indexing, integration, structure termination, structure refinement, all of those are sort of just ballpark estimates. But within about an hour and a half of taking your tilt series, you can theoretically get your structure out of it. So micro ED does hold a lot of promise for doing small crystals. So the other part that I wanted to talk about, so how was this data collected? So of course we used serial EM to drive everything. So this was also done with continuous tilt, so there's no stopping. And we did a couple of things. So this was about 20 frames per second for the entire movie. It's a 2-minute exposure from plus minus 50 degrees. We did 2x hardware binning because with the 8K physical pixel size, it's not so important. It's quite a large field of view. If we run it, in bin 2 hardware, we can get higher frame rates, a little bit better noise performance. But at the same time, the images are much smaller, and so the 8K images take up quite a lot of space versus the 4K images in bin 2, and it just makes for a little bit better time in terms of data processing. Let me see. I saw a quick question. Yeah, yeah. So this is in fact on the detector itself. This is on a direct detector. This is on a DE64. Yes, people are obviously worried about damage. Like most things, if you're doing electron diffraction, you're going to be using the beam stop. The beam intensity, obviously, for micro-ED is very different than any of the other diffraction techniques for the electron microscope. But yes, there is a certain risk of damage should the the unscattered beam sort of move away from the beam stop. But there's it's the risk versus reward. Most of the time, if there's an accidental exposure with in diffraction mode, the damage is not permanent. And typically we'll work fairly closely with our customers that are trying micro-ED. But one of the main benefits that I'm going to talk about is the very last point on the slide, which is this global shutter. So this is mainly for material science in terms of the way that it functions, but every camera out there is based on CMOS uses a rolling shutter. So a rolling shutter basically looks like, let's see if I can get this through. Looks like this. So you have your sample on the left-hand side, which is something that's going to be moving, whether it be the beam or motion, things like that. When you are reading out from the camera with a rolling shutter, you read from the very top row to the bottom row. And there's a time difference between the two. If you have an object inside of your field of view that is moving, then with the rolling shutter, if it's moving either too fast or it's moving in a particular direction, then you end up with artifacts in it. So it's either going to have a gradient across the image, it's going to look strange. It could be in 2 places at once. You could have signal left over from the previous frame. And so this is the way most things work. For most exposures, it's not a problem. If you're just looking at small particles that are in ice that don't really move anywhere, it's not such a big deal. It's something that you don't really notice. But when you're talking about a diffraction pattern, that's where things become important, because the intensities for the diffraction spots, that's the information, right? That's what's really important. And so if you're getting a gradient from those spots from one frame to the next, then you're losing information, or you're contaminating the next frame with information from the previous area. And with a global shutter, you read out from all the pixels simultaneously. There isn't any delay. So the 2 benefits for this is that you can synchronize with like a diffraction pattern. But mainly for something like, say, material science, you can synchronize with the scan. And so that's the benefit of a global shutter, is that if you have an object, or if you have, in this case, a diffraction pattern that's moving and changing as you're doing this continuous tilt, then with the global shutter, you can capture exactly all the intensities from that position all at the same time without any streaking artifacts from one frame to the next. For something like material science, we're talking about like 4D STEM. Basically, you can think of it as that as you're scanning across an object or your sample, then every single spot is a diffraction pattern, and only one diffraction pattern if you have global shutter. And so this is, again, part of the this hardware approach that we've taken is to minimize noise, to maximize flexibility, is that when you're doing these kind of experiments, if you don't have the global shutter, then your data is lesser quality. and people want the best quality data, right? And so, you know, for some types of experiments, especially, you know, micro-ED, you know, diffraction in general, then, you know, the rolling shutter is not something that you want to be, you know, have to be stuck with. A global shutter is really what you have to have. I think that pretty much comes to the end of all of the talk for today. There's a lot of people that were involved in, you know, the data that I presented from a variety of different universities, from Stanford, there's from Lawrence Berkeley, Bob Laser discussions, you know, Scott Stagg at Florida State, and of course, you know, cryo-arm folks at Glasgow, and a lot of people from JOL, both in the UK, US, and from Japan as well.
I just have to thank you all for being with us today, and hopefully we'll see you again in the next webinars or when I visit you sometimes. Have a very good day. Cheers and goodbye. Thanks, Michael, again.
All right. Thank you very much.